If you dive straight into a black hole, you don't get instantly crushed into dust. Instead, you experience a warping of physics that splits your reality into two distinct stories. We are taking a trip to the supermassive black hole at the center of our galaxy, Sagittarius A star. It holds the mass of over 4 million suns. To track the mechanics of this freefall, we have to establish whose clock we are reading. This split-screen diagram shows the exact same event from two perspectives. If a friend watches your dive through a telescope on Earth, they see you slow down. Eventually, you freeze right at the edge. The light bouncing off you stretches out, shifting your image into a deep red hue until you fade into the black. Extreme gravity dilates time for anyone watching from the outside. From the perspective of a telescope, the rest of the universe will never see you cross the threshold. Look at your own wristwatch, though, and the seconds tick by normally. You don't freeze. You keep falling. These two realities exist because of Albert Einstein's general relativity. Massive objects bend the fabric of space and time to such a degree that your position in a gravitational field dictates the speed of your personal clock. We are leaving the telescope behind. We are now locked strictly to your chronological point of view, heading straight down. A supermassive black hole operates on a staggering scale. You could fit millions of our suns inside its diameter. Because all of that mass is distributed over such an immense volume, your initial approach toward the edge is peaceful and smooth. You cross the event horizon without feeling a single thing. There is no physical barrier, no sudden bump, and no immediate spike in gravity. The surface gravity of a supermassive black hole is spread so widely that the tidal forces at the very edge remain too weak to notice. But the mathematics of your environment have changed. You are trapped. This 3D grid illustrates the river model of a black hole. Far away, the grid is still, but as you get closer, space itself acts like a waterfall flowing inward. Once you cross the event horizon, that grid plunges downward at speeds exceeding the speed of light. Fire your rocket thrusters all you want. Even if you accelerate straight out toward the exit, the speed of the river carries you backward into the dark. Moving toward the center is no longer a choice of direction. It is a mandated trajectory driven by the collapse of the universe's geometry. Your peaceful drift eventually hits a limit. Physicists call this depth the ouch time, the point where the space-time weather transitions from calm to lethal. This diagram shows the mechanics of tidal acceleration. As you fall closer to the center, the gravitational pull on your feet becomes exponentially stronger than the pull on your head. Your body is stretched vertically, while the space around you is crushed horizontally. This process, known as spaghettification, breaks your body apart down to the individual atoms. An alternative model paints an even more chaotic picture. The egg beater theory predicts that space-time oscillates here, randomly stretching and squeezing your remains in all directions like an electric mixer. Long before you reach the absolute center, human biology is dismantled into a stream of separated subatomic particles. We follow those torn-apart remnants as they arrive at the absolute center, the crunch point or singularity. We often picture the singularity as a dense physical object sitting at the bottom of a gravity well. This graph maps space on the horizontal axis and time on the vertical axis. Because space-time is distorted so heavily inside the horizon, the singularity becomes a moment in time. This makes the singularity your unavoidable future. Trying to swerve around it is like trying to run away from tomorrow. At this crunch point, time as a measurable coordinate ceases to exist. All that remains is an incomprehensible bubbling of quantum foam. The singularity marks the point where the mathematics of general relativity can no longer describe reality. Your body is gone. Time has ended. So what happens to the core subatomic information that used to make up you? This creates a contradiction for physicists. Einstein's equations dictate that your information is destroyed, but quantum mechanics dictates that information must be preserved. Stephen Hawking suggested a potential middle ground. Black holes slowly leak radiation, returning your scrambled information back into the universe over billions of years. Alternative theories propose that the interior connects to a wormhole, depositing your scrambled data into an entirely different region of spacetime. While black holes dismantle human biology, They represent the only environment where our conflicting theories of the universe are forced to occupy the same space.